Good morning, everyone. Most of you will be watching this video after the fact, which means you'll not be watching it live. As the title suggests, beneath my little picture there, I'm Lucian, and I will be your tutor for today. Today we will be covering, let me just here. Okay, we'll be covering tutorial number 3, question 1. This tutorial is on the laws of motion and uniform circular motion. Okay, now I'll be doing questions 1 to 5, while tomorrow Arnold will be doing 1 to 6 to 10, and then on Thursday we'll have James finishing up with 11 to 15. Okay, so today, question 1 is on Newton's laws. Okay, it's on tension and force diagrams. Okay, well, force diagrams will come in handy to solve these problems. So let's, without any further ado, start question 1. Okay, I'm going to share, for those of you who are only joining on Teams, I'm going to share my screen now. Okay, can you guys on Teams just give an indication if you can see my screen now? Just a thumbs up. Felicia, and I can't see the other name. It's okay. Thank you. Okay, great guys. Okay, now as always, before I start, feel free at any point to stop me and ask questions. Okay, now the first question here is the following. It states, okay, it's a question 1. It says the systems shown below are in equilibrium. Now, they did not include the images that we're going to use. These systems are the ones that's supposed to be below this. Okay, so the systems shown below are in equilibrium. So all of these systems, A, B, C, D, they are all in equilibrium. Okay, these two balls are holding each other in equilibrium. This ball is in equilibrium. It's not pulling the wall, and the wall is not pulling the ball. Okay, these two are in equilibrium, and this block is on this inclined plane in equilibrium. Okay, meaning it is not moving. There is no resultant force. Okay, it can be moving but at a constant velocity. Okay, now if the spring scales are calibrated in newtons, now each one of these things here, this one here, this one here, here, they are all spring scales. Okay, they measure force. Okay, they measure force. Now they are asking you to measure what each one of those spring scales will read. Okay, what will they display on their monitors? What amount of force will each one of those spring scales display on their monitors? Okay, now they say tell us to ignore the masses of the pulley and the strings and to assume that the pulleys and the incline in the figure are frictionless. Okay, so we assume no friction, and we assume that the pulleys and the incline are frictionless, and we assume that the pulleys and the strings have no mass. That's what we assume. Of course, in reality, they will play a role because they add to the masses. Okay, now question 1. We're going to work out the forces on each of these springs A, B, C, D. We will work out the force on each of those spring scales. Okay, on each of those spring scales, we'll work out the amount of newtons using Newton's laws of mechanics. Okay, now let's just say for the first one we have this setup. Okay, we have a table, two pulleys, and two 5 kilogram balls. Okay, so let's say this is A. This is A. Let me just, I'm going to draw a rough sketch of each one of these things. Okay, forgive me, I am no artist. So I will draw a rough sketch, really rough. Okay, so there we have the pulleys. Okay, we have the rope connecting these two pulleys. Okay, it goes down, and there's a 5 kilogram ball hanging on both sides. Okay, there's a 5 kilogram ball there and a 5 kilogram ball there. Okay, so we have this situation. Okay, I just drew that, and I, of course, I still need to draw in the scale. Okay, the scale, it measures the force. Okay, we need to determine what is the force in this scale. Okay, this spring scale. Okay, so first of all, in question A, this question for A, okay, we need to one isolate one of these masses. Okay, let's pick the one on the right. I'm going to pick isolate. So first of all, isolate one of the masses. Isolate one of the masses. Oh, my handwriting is terrible, but just listen to what I say. Okay, so we need to isolate one of the masses. Okay, so let's pick the one. I'm going to pick the one on the right hand side. Okay, so on the right hand side. Yeah, I'm going to pick the one on the right hand side. You can pick the one on the left hand side. What, we're just going to isolate one of these masses. Okay, so isolate either mass. Then what you do is, what is there? You can draw for that particular mass. You can draw for that mass. You can draw for that 5 kilogram a force diagram. Okay, for that mass you draw a force diagram. Okay, a free body diagram. Okay, I'm saying a force diagram, a free body diagram. Okay, so what will be in this force here? It'll be, what is holding this ball up? Of course, let's start with the obvious. There will always be the force of gravity pulling it down, and that force of gravity, remember, this is a 5 kilogram ball, so that force of gravity is equal to 5 kilograms multiplied by 9,81. So let's plug that in into our calculator. Let's plug it in. Where's the calculator? There it is. Underneath is 5 multiplied by 9,81. We have 49. Okay, so let's just go with 49 newtons. So we have 49, a force of gravity of 49 newtons. Now we need the tension. Okay, so we need the tension now. This is the tension and this is the force of gravity. These are the two forces acting on this ball on the right. Remember, we just isolated one of them. Okay, we just isolated one of them. Okay, okay, Gloria, you have your hand up. You can ask, or you're going to type. Yeah, don't be shy. If you have a question, you can ask. Or was it just a mistake? She just left the meeting. Okay. Uh, so, she's back. You have a question? If you if you have a question, you can just ask. At the risk of this sounding like a cliche, this is a safe space. Okay, I'm going to continue. Okay, so now we have this on this ball here. Okay, remember we're just picking this ball here. Okay, we're just picking this one here. Okay, We isolated just one of them. Okay, we can work with both, but that is just cumbersome. Okay, so we're working with one of them. Okay, so the right hand side, we have two forces acting on this ball: its own weight, the force of gravity, Fg, and the tension in the rope pulling it back up. Remember, it's in equilibrium. The forces must always be balanced. Okay, now since it's in equilibrium, we know that the force of tension, since you can write it there, since equilibrium is established, we know that the tension plus the force of gravity, which is just the mass times acceleration, is equal to ma, which is the net force, sorry, the tension plus the force of gravity should just equal to, remember this is the sum of the forces. This is basically saying the sum of all the forces is equal to the tension plus the force of gravity, because there are only two forces acting on this ball. That should equal the mass times the acceleration. Remember, F is equal to ma, F is equal to ma. And ma, since this ball is not moving, its acceleration is 0, so that should be 0. Basically what we're saying is the tension plus the force of gravity should be equal to 0. Okay, now this scale in this case is reading the tension. Okay, it's reading the tension. Okay, the scale reads the tension. Let me write that in the scale reads the tension, T. Okay, so we have T plus mg is equal to, the scale reads the tension, and we have T plus mg is equal to 0. We know we want T, we know that mg is equal to, we're taking up as positive. Okay, we're taking up as positive, so mg should be down, it's 49. It's going down 49 newtons. The weight is downward, so it's negative 49, so it should be plus, and the weight is negative because it's opposite direction. That should be 0. So the tension is equal to 49 newtons, and that is upwards. Sorry, that's 49 newtons and it's upwards. Okay, that is the tension. Okay, so the tension is 49 newtons upwards. So the tension is 49 newtons upwards, which means the readout on the scale, okay, is 49 newtons. So here we will have a measurement of 49 newtons. Remember, you could pick either one of the balls. Okay, now many of you might be tempted to, let's just check. You see, the first one, A, is 49 newtons. Okay, that's the answer. Now, many of you might be tempted to multiply it by 2 since there are two balls. Okay, it's the same tension in the rope because it's the same rope. Okay, the tension runs all through this rope. It is running through this rope. Okay, so it's 49 here, 49 there, 49 there, 49. So the tension in the rope is 49 newtons. Okay. Now we go for number B. Okay, B. B is this setup here. This is B. Okay, we need to work out the measurements on that scale there. Okay, so basically same thing. So we can the force, if we were to draw the force diagram for B, let's just say for B, we have the force, the free body diagram is going to be exactly the tension on that ball there. It's going to be the tension on it and its weight, which is 49, the force of gravity, which is 49 newtons. So the tension is going to be exactly the same. It's also going to be 49 newtons. It's going to be the same as the previous problem. Okay, that's why I'm not working it out. It's going to be exactly the same as the previous problem. Okay, the tension in the rope is going to be 49 newtons, meaning the readout on the scale is going to be 49 newtons. So the answer, I can just write here, answer is the same as in A. So it's going to be exactly the same as in A because it's exactly the same situation. Okay. In this case, we have in A we have another ball balancing the 5 kilogram weight. In this case, we have the wall balancing the 5 kilogram weight. Okay. Now we move on to number C. Okay, let's go to C. Okay. C, the force diagram in C, wait, is here. I just picked it up. Let's go to number C. Okay, first of all, let's check the answer for B. It is also 49 newtons. Okay, 49 newtons as well. Okay, now, of course, if you have any questions, please let me know. Now, let's go to part C. Here we have a pulley with two blocks hanging on it. Let's just draw the free body diagram for this situation. We have a pulley and then we have two forces downward. Okay, so we have the pulley, then we have a force and a force. Okay, and these two forces are the forces of tension, tension 1 and tension 2. And then we have the scale here. Okay, so in this case, you can isolate either mass again. You can isolate either mass. Okay, so this one is a 5 kilogram, that's also 5 kilograms, so you can pick one of them. Okay, same as before. Oh, that is the hard part. Or you can just easily just isolate the pulley, the whole pulley system. So this whole part, isolate that part. Okay, there's the mass also. This here should be tension number 3. Okay, tension number 3. Okay, so we have tension 1, tension 2 and tension 3. Okay, tension 3 will be the readout on the scale. Okay, tension 3 will be that readout. Okay, so we isolate the pulley. Let's isolate the pulley. My notes is a bit. So we have tension 3 plus 2 times those tensions, tension 1 and tension 2. 2 times tension 1 or tension 2, we can call them just T. Or let me just rather write it this way, plus tension 1 plus tension 2 should be equal to, that's the sum of the forces. The sum of the forces is equal to tension 3 plus tension 1 plus tension 2. Okay, and that should all equal to the mass times acceleration according to Newton's law. And since it's not moving, it is 0. So the tension 3 plus tension 1 plus tension 2 is equal to 0. Now we know that tension 1 and tension 2 are exactly the same because they have the same 5 kilogram blocks hanging on them. So we can actually say tension 3, which is what we want, is equal plus 2 times tension 1, the magnitude of tension 1 is equal to 0. Okay, now let's work out tension 1. What's the tension in the first block? Okay, so it's going to be T3 is equal to 2 times the mass times the gravitational acceleration of tension 1, which is the mass is 5 kilogram block. It's a 5 kilogram block, and the acceleration is 9.1. So that's 2 times 49, that's 98. So remember, this goes over, okay? They should be equal because the tensions going downward should be exactly equal to the tensions going up. The sum of these two should be 0. So T3 is equal to 2T1. Okay? So that is equal to 2 times 5 is 10 times that's 98 newtons. So we have 98 newtons, that's T3. And that is the readout on the scale for the pulley system. Okay, so there it is 93 newtons. So 93 newtons on that scale. Sorry, not 93, 98 newtons on that scale they have there for T3. I mixed up I wanted to say T3 and then 98 and ended up saying 93. Okay, so the final situation, the incline. Okay, the incline. What is the So now we have determined that this one is 49 newtons. We have determined that that one is 49 newtons. We have determined that this one is 98 newtons. Okay, we now need to determine what is that value there. Okay, let's go check here. Okay, according to the answers, the third one is 98, yes. And if we check there quickly, we should find that the fourth one should be 24.5 newtons. Let's see if we get 24.5 newtons on that readout. Okay, so let's go to situation number D. Okay, let's draw the force diagram first of all for system number D. Okay, where's my force diagram? My force diagram for system D is we have this block. For that block, remember, we have this 5 kilogram block there. We have a 5 kilogram block on an inclined plane, okay, at 30 degrees to the norm. Okay, so let me try and draw the force diagram. So the force diagram is going to look like this. There's the 5 kilogram block. That's the force diagram, not the free diagram yet. I'm just drawing the what should be there. There's the spring scale that's measuring the force. There's a piece of the wall. The block is sitting on the wall while this inclined plane, and this inclined plane is making an angle of 30 degrees. Okay, so you need to find the tension in that table there. Okay, so let's draw a force diagram quickly. Okay, the force diagram is going to look like this. So we'll have the force of tension here, the force of tension holding this block steady. Of course, we always have the block's weight pulling it down. It's a 5 kilogram block, so there's 49 newtons of weight. And then we always have, of course, the normal force, okay, pushing upwards against it, the normal force. Okay, so there's your force, your free body diagram. Okay, now let's work on this problem. We know that the sum of all the forces in this situation, okay, the normal plus the tension plus the gravitational force should always 0 because it's in equilibrium. Okay, now we'll focus on the component along the incline. Okay, along the incline, because the tension is what's going to give you that measurement in the spring scale. Okay, so along the incline we have the x component of the normal force, plus the tension, which only has an x component, plus the x component of gravity, its x components. So all the x components of all these three forces, okay, only the x components, meaning the forces running parallel to the inclined plane. Okay, they should all be 0. Okay, now the normal force has no, if you look here, the normal force has no horizontal components. Okay, it has no horizontal components. It's 0 newtons. Now the tension is what we want. We have T, it's going that way. And then this force here, the gravity, the gravitational force has a horizontal component, and it's going to be the mg times the sine of 30 degrees. Okay, remember we want this component of the force, and that's going to be 30 degrees, so this is the sine over the gravity. Okay, so it's going to be opposite over hypotenuse, which gives me sine, and that should all be equal to 0. Okay, so the tension then is equal to mg times sine of 30, and that mg is now none other than 49 newtons. Its the tension is then equal to mg times the sine of 30 degrees. So basically in this first diagram, the tension is just going to be equal to the horizontal component of the weight. Okay, so it's going to be mg times the sine of 30, and the sine of 30, you can plug that into your calculator. You will find that this comes out to, you work it out, the sine of 30, if I remember my special, it's over, let me rather not do that, I can't remember my high school math, my special angles. So let's do on the calculator, which is advisable. Don't try to do what I do. 49 multiplied by the sine of 30 degrees, 24.5. Okay, so the answer is 24.5. So the force that should be on this uh, scale is 24.5 newtons. Okay, so we've worked out the forces on each of these scales, and they are exactly as what the answers should be. Okay, now we are done with question 1. Okay, question 1, we are done with it. Are there any questions pertaining to question 1? If there are, please ask them now before I continue with question number 2. And all of these questions you'll find is more or less the same. Well, not that you have to work, but you're going to have to apply Newton's laws and draw free body diagrams. Okay? If there are any questions, please raise your hand. If not, I will continue. Okay, Dudu, sorry, I just saw your thing now. You say you can't hear me. I don't know, but others can hear. Can other people in the online space, please let me know if you can hear me. Either on the guys on Teams, I know you can hear me. Uh, YouTube, can you guys hear me? Can I get a reaction from anyone in YouTube if they can hear me? Okay, Mr. Mube or Mrs. Sorry, I apologize. I don't actually cannot see like in Teams if there's Mr. or Mrs. Okay, so Mr. or Mrs. whatever you identify has just told me that he can hear me. So Dudu, I think there is something with your earphones or your laptop or whatever, but the others can hear me. So the problem is not on my end. Okay, guys, I will continue with question number 2. Go. Uh, thank you guys for answering. Okay. 2. Question number 2. Okay. I know it is not ideal to be spending your afternoon doing physics, but I appreciate the effort nonetheless. Okay. Okay, question 2. The question is, three objects are connected on a table as shown in the figure below. Now, for some reason, these questions do not put in the figures that they are referring to. Okay, now I'm going to draw the figures. This is the figures that should have been included. Okay, this is mass number 2. Then it is connected via a pulley. Okay, to two other masses. Okay, to two other masses. Okay, this is M1 and this is M2. This is the situation. M1. Oh, sorry, this is M3 now. This is M2. So we have M1, M2, and M3. Okay, and they are saying the coefficient of kinetic friction between the block of mass M2. So the coefficient of kinetic friction, meaning mu k is equal to 0.350. So the coefficient of kinetic friction mu k is equal to 0.350. Okay, now the objects have masses of m1 is 4 kilograms. Okay, so m1 is 4 kilograms. I'm not going to write 0.00, but m1 is 4 kilograms. M2 is equal to 1 kilogram, and then M3 is equal to 2 kilograms. So 2 kilograms. Okay, I'm moving it upwards now. So we have these three masses connected on both sides. M2 is connected on both sides by M3 and M1, and the kinetic coefficient of friction between the block M2 and the table is 0.35. Okay, and the pulleys are frictionless. Okay, so there's no friction from the pulleys. Okay, they saying number 1. Okay, so 1, draw a free body diagram. Draw a free body diagram of each object. Okay, so free body diagram of object 1, object 2, and object 3. Okay, so a free body diagram, let me see. So for M1, this is for M1, we have the force of tension pulling it up, but its own gravity pulling it down. Okay, so its weight is just the weight of M1. We have the force of tension, the tension on 1 due to block number 2. So the tension on 1 due to block number 2, not the tension of 12, it's the tension of 1 due to block number 2. And then it has a weight. This is block M1. Remember, this is M1. We're just drawing the free body diagram. Okay, and it has a weight pulling it down at a speed of 9, its mass times gravitational acceleration. Okay, now for block 2, M2, it has multiple forces on it. Okay, first of all, it has a normal force on it. Okay, that's the easiest one. It has a normal force on it. Okay, then it has its weight on it, its force of gravity, so the mass of 2 times the gravitational acceleration. Then it has the tension of 2 due to 1, due to block mass 1. It has the tension of 2 due to 1. Okay, it's the same tension, T12 and T21. Let me just call it T12 so that you know. Okay, it's the tension of block 1 on block 2, the tension due to 1 on 2. Okay, then it has one other thing. Okay, it has the tension due to block 3, and it also has friction. Okay, remember it has friction because they are given us a force of friction. Okay, so the friction is just mu k times the normal force. Okay, since we don't know what the friction is. But why? Can you guys answer me why I have drawn the friction on this side and not on this side? Remember, they just say there's friction. Okay, in this case, okay, block M1 is heavier, it is 4 kilograms. So I am assuming this whole system is sliding this way. Okay, so if the force applied is in this direction, so the force applied is in that direction, then that means the friction must be in the opposite direction. Okay, that's just a hunch based on what they have told us, so not really a hunch. Then for block number 3, it just has the tension due to 2 on it, and then it has its own weight, which is just its mass times the gravitational acceleration. And now we have the free body diagrams for these 3 blocks. Okay, so we have the free body diagrams for these 3 blocks. The next question is determine, the next question, number 2, is determine the acceleration of each object, including its direction. Okay, so determine the acceleration of each object, including its acceleration. So I'm going to do that on the next page. Okay, so here, number 2, determine the acceleration of each one of those blocks. Okay, and I'm going to keep, this is the force diagrams for each of them, and I'm going to determine the acceleration for each one of them. Okay, uh let me just remove this page here. So here we have, okay, so now let me indicate we've indicated all the tensions. Okay, so we have all the tensions indicated here on this free body diagram, T12, T23, T23. Okay, so those are the 2 tensions. Okay, then we will represent the acceleration with A. Okay, A, the acceleration by A. Okay, so we can call. So let's go. Now for mass 1, for mass 1, okay, for mass 1, okay, this is mass 1, this is its force, its free body diagram. Okay, it only has the tension 1, 2, and its weight acting on it. Okay, so for mass 1, we have that the sum of the forces in the y direction is equal to the mass times its acceleration in the y direction. So the sum of the forces in the y direction is equal to the tension T12, which is the tension on that mass here. The tension T12, it's the tension in the string going upwards. This tension in the string here, the tension. Okay, so that's T12. So the tension, the tension minus the weight, since it's going down, the weight is in the opposite direction, so its weight is the mass of 1 times the gravitational acceleration. That should equal to, the gravitational acceleration is negative, so it should equal to negative m times the acceleration, negative m1 times the acceleration. Okay, now for m2, I'm just setting up a whole bunch of equations now. For m2, we have that there are multiple forces. The same thing, the sum of the forces in the x direction. Remember, this is m2. We have x direction. The forces in the y direction cancel, the normal and that cancel. Okay, so the sum of the forces in the x direction, let's just first say the sum of the forces in the y direction for for m2 is equal to ma, mass times acceleration. Now the sum of the forces in the y direction for m2 is just equal to the normal force minus m2's weight, and that is actually equal to 0. Okay, because it is not moving upwards or downwards, it's stationary, it's just sliding on the table. Now the sum of the forces in the x direction is equal to ma, the acceleration being the exact same as that acceleration there. That's not a 9, that's an a. Okay, so the sum of the forces in the x direction, here we have the forces in the x direction is T1 to T2, the tension in the cable on the left hand side, the tension in the cable on the right hand side, or cable or rope, and the friction, of course. So let's pick which one can we can choose either one as positive. Okay, so let's choose to the left as negative. So we have the tension 1 2 is negative, and then we have positive the force of friction uk times n plus T23, that is equal to m, that is still a negative acceleration. It's going to have the same acceleration times, it's going to have the same acceleration negative as this one, because it's going to be accelerating in that direction towards the left. Okay, so now for m3, beautiful car by the way, we have the sum of the forces in the y direction is equal to mass times acceleration in the y direction. And so the sum of the forces in the y direction for 3 is just the tension 2 3 minus its m3 times its acceleration, and that is equal to positive, because since it's accelerating upwards, positive m3 times a. Okay, so there we have 3 sets of equations. Okay, now we can just solve all of them. Okay, so we have 3 simultaneous equations. Okay, let's see. This is 1, this is 2, and this is 3. 3 simultaneous equations. Okay, let me write all of them down for underneath each other, then you'll see them all. We are left with 3 simultaneous equations. This gives three simultaneous equations. This gives 3 simultaneous equations. So the 3 simultaneous equations are then T1 2, the tension in 1 due to 2. Sorry, I'm touching the cable here. The difficulty I'm writing at the end of the page. T1 2 minus M1 G equals to negative M1 acceleration. The next equation is T1 2 negative T1 2 plus mu k n plus T23 equals to negative M2a. Then the last one is T23 minus M3G equals to M3A. Okay, so those are the 3 equations, the 3 simultaneous equations. Now if you add all of them up, if you add these equations up, you will see that the tensions cancel. That's a positive there. Sorry, there. This one is going down. The tension is going somewhere. I made a mistake. Let me just check here. Oh yeah, here should be a negative here. That is going negative. Wait, I need to choose. One of them is positive. This one is choose upwards is positive. That one is negative. So that way is positive. Yes. Okay, so that way is positive, positive. So this tension here should be negative. Okay, I just made a quick mistake there. So we are choosing towards the right as positive, then towards the left as negative. Okay, just make sure about this thing here. Okay, so we have that this one is positive. This one here is negative because it's towards the left. That one should be positive, and its acceleration is positive because it's negative, should be negative. So there we have it. Okay, so if we add all of them up, we have that this one should be negative now, that's positive. Now if we add all of them up, remember to choose and don't forget to indicate which direction is positive and negative. Okay, so if we add all of them up now, let me just recap. Okay, this is the situation we're stuck with here. This is the situation. Okay, I have chosen this direction as moving all around this direction as positive and this direction as negative. Okay, so we have this force here will then be going towards that way, so it will be positive, and this one is negative, and that's what we indicated there. It is positive and then it is negative m1g. Then we have that here t12 will be negative, and that's what we have. Those two will be positive, and that is what we have. The acceleration will be towards the left, so it will be negative. In that case, the acceleration is also downwards, so it's negative. Then here we have towards the left, the tension towards the left, the force is going upwards, so it is negative. Then we have the weight is going downwards, which is positive, and then it will be accelerating upwards, which is also negative, in the negative direction. Well, it's not negative acceleration, it's in a negative direction. Okay, you can choose, you could have chosen either way, if positive or negative. Okay, now let me continue. Okay, where am I now? Okay, if I've written on one of these pages, this one, this one is my page. I now have these three equations. If you add them up, you have T1 minus. If you add these three up, you remember this is a simultaneous equation, so you are allowed to add them all up. They are simultaneous equations. Okay, Ty, this tension cancels with this one, this tension cancels with this one. What you're left with is m3g, m3 times the gravitational acceleration minus m1g plus mu naught kinetic coefficient of friction. This is just the force of friction is equal to, and that all is equal to m1 negative m1a negative m1a negative m2a plus negative m3a. That's equal, that's what left. If you add those three up, that's what's left. Now, of course, you can take out the acceleration and the negative sign. You can take those two out, and you'll have that the three mass is m1 plus m2 plus m3. That is equal to 4 kilos, 4 kilogram plus 1 kilogram plus 2 kilogram on that side times the acceleration, and on this side you will have all the tensions have cancelled, so you'll have the m3, that is m3 is 2 kilogram multiplied by 9,81 minus 4 kilogram multiplied by 9,81 minus 0.3. What is the coefficient of friction they gave us? It is scroll down. They gave us is the kinetic friction between the blocks in the table is 0.350. 0.350 multiplied by its weight. The weight, the normal force, is equal to the weight. Remember, we had an equation for that, which stated that the sum of the forces in the y direction, the normal force minus the weight, should be 0. So that's the weight of 2 now. So it's the weight of 2 is equal to 2 times 9,8. And if I check correctly, 2 times 9,8, it is 19.6. Now its weight is 1. Let me just check. What is its weight? Its weight is 1 kilogram. So 1 times 9,8. So the force of the normal force is 9,81 Newton. Okay. So if we work that all out, we have on this side negative 8 times 4 plus 1 plus 2, that's 7 kilograms. And on this side, we have a force of 39 minus 3.43 minus 19.6. So we have 2 times 9,8, that's 19.6 newtons, minus 4 times 9,8, 19.6 doubled is 39.2 newtons, and then we have minus 0.34 multiplied by, that's 3.43 newtons, and you divide that all by negative, that gives you a negative answer. You divide it by negative 17. You can go and work out your acceleration now. Okay, you add all of these, you subtract them all from 19, you get a negative answer. Add them all and then divide by 7, and then you'll find that your acceleration is 2,31 meters per second squared. Okay, so this whole system is moving at 2,3 meters per second squared. Okay, now question number 3 is determine the tensions in the two cords. So you need to determine T23 and T12. Okay, so you need to determine the tensions in the three chords. Okay, so the tensions in the three chords, two chords. Now, we've worked out everything. You can just work out one of the equations. Okay, remember we originally had an equation which says that negative T1 plus 39,2, which is the force of its weight, is equal to 4 kilograms multiplied by the acceleration of 2,3. That's this is this equation here. Let me just quickly. That's the first equation here, this one. Okay, we are just filling in all the values that we know. 2,31. Is it 2,31? Let me just check. Yes, meters per second squared. Okay, now if we solve for the tension, we have everything to solve for the tension. The tension T12 is equal to 30 newtons. Let's check. So the answer, we draw the free body diagrams. The acceleration was 2,31 meters per second, down for M1, left for M2, and up for M3. Okay, so that's good. And then T1, we just worked out to be 30 newtons. And then let's see, T2, T23. Okay, we use this equation here, T23, this equation here. We'll be using this equation here, the last one, T23, negative T23 plus M3G is equal to negative M3A. Okay, so negative 23 plus M3G, which is its weight, is equal to negative M3A. Of course, you can divide all the way through by 0, which will just give you, if you divide by 0 throughout, you will get 2, 3. This is the equation that you just determined earlier on, okay, for block number 3. It is block number 3, yeah. So if you divide by negative throughout, you'll get M3G equals to M3A. So this is what we want, the tension. We have that this mass, we worked it out earlier on. I just scrolled unintentionally down. Okay, we worked out the mass. M3 times that force is 19.6 newtons. M3 is 2 kilograms and the acceleration is 2,31 meters per second squared. Therefore, if you solve for the tension, you have that T23 is equal to 24.2 newtons. So the tension is 24.2 newtons, the other tension. You work it out. So they have 22.3 is 24.2 newtons. Okay. Now they're asking us, if the tabletop was smooth, okay, would the tensions increase, decrease, or remain the same? Okay, so if the tabletop was smooth, if the if the tabletop was smooth, so if the tabletop was smooth, if the tabletop was smooth, then the acceleration would become larger because there's no friction, meaning the applied force is larger. So if the tabletop was smooth, the acceleration would become larger. So the acceleration would become larger. And if the acceleration becomes larger, T12 would increase and T23, okay, sorry, this one would decrease. The original one, the tension would decrease and the next one would increase if the acceleration becomes larger, right? Because of these equations. Okay, because the tension here is equal to, the tension here is equal to that minus this. Basically, if you divide throughout by 0, the tension would be, if the acceleration increases, if the acceleration becomes larger, here in this side the tension would decrease and it will increase in the bottom one. Just some dimensional analysis there that was required. Okay, so moving on. If there are no questions, I will move on. If you have any questions, please stop me and then ask your questions. Otherwise, I will have to continue, or not will have to, I will continue. So, question number 3. A car is traveling at 50 miles an hour on a horizontal highway. So a car is traveling 50 miles an hour on a horizontal highway. They're asking, number 1, if the coefficient of static friction between the road and the tires on a rainy day is 0.1, what is the minimum distance in which the car will stop? Okay, so this is some of the work that we're going to do. Okay, so question number 1 and 2. So applying Newton's second law, applying Newton's second law. Applying Newton's second law, we have that. We applying Newton's second law to the car. We have that to determine the maximum static friction force. Okay, so we are going to determine the force of friction. So the force in the y direction, okay, so on the road is equal to the sum of the, is equal to the mass multiplied by the acceleration in the y direction. Okay, that's just Newton's law, second law. Now there are two forces in the y direction, okay, on this car. Let's say this is the car we're going to draw. This is the car. This is its free body diagram. It has the normal force, it has its weight, which is the force of gravity, it has the force applied to it by its engine, and it has the force of friction. Okay, that is the free body diagram. That's the free body diagram. Okay, now the sum of the forces in the y direction is equal to the normal force minus the the force of gravity, which is its weight, and that is just equal to 0 because the car is not moving in the normal, in the vertical direction. Okay, now the sum of the forces in the x direction is equal to the mass of the car times its acceleration in the x direction. Okay, now the only force that is acting, a car is traveling on and if the coefficient of static friction between the road and tire on a rainy day is, what is the minimum distance in which the car will stop? Now the force acting on the car on this rainy day is the force of friction, static friction. The force of friction, and it's equal to the mass times the acceleration. Okay, now the maximum acceleration that this car can have, the maximum acceleration that this car can have, acceleration is, the maximum acceleration that this car can have is equal to, remember it's equal to, the acceleration is the force of friction, acceleration is the force of friction which is negative, divided by the mass. Now the force of friction in this case is equal to, how do you get the force of friction? It's mu s times the normal force, and in this case the normal force is equal to the weight, which in this case is mass times gravitational acceleration over the mass. So the masses cancel, so the maximum acceleration is equal to the coefficient of static friction multiplied by the gravitational acceleration. Okay, so that is the maximum acceleration that this car can have, since there is no applied force. Okay, now the initial and final conditions are, now x position initially is 0, its final initial velocity is 50 miles an hour. Now I'm just going to go ahead and switch that to kilometers per hour, to meters per second, sorry, 22.4 meters per second. And then its final velocity, it comes to a stop, which means it's 0 meters per second. So you have initial velocity, final velocity, and its initial position. Okay, and they want the, what is the minimum distance? So they want the minimum distance means the maximum acceleration, the maximum deceleration is the minimum distance. Okay. So maximum friction, maximum deceleration, or maximum acceleration in the opposite direction will give you the minimum distance it stops. Okay, and we want xf, the final velocity, the final not final velocity, the final position. Now we know from our equations of motion that v squared is equal to v final squared v initial squared plus 2 times xf minus xi. Okay, now v initial in this case is equal to 2 times the coefficient of friction times g times xf, because that is 0 and that acceleration is just equal to, that is negative, that is just this one, v naught is 50, vf is 0, so that's squared. If you solve for this thing, you will get that this is the formula that you're going to be working with, because this is 0, this is going to be what we want. If we take it over, it becomes negative, so it'll be negative 2a, and then since acceleration is equal to negative mu sg, it is just going to be positive mu sg, so it's positive mu sg times 2 times the final acceleration. So you just solve for the initial velocity. Okay, plugging in everything that you have been given so far. So now we have the equation v initial squared is equal to 2 times the coefficient of kinetic friction times the gravitational acceleration times final position. Okay, that is your final velocity, your initial velocity. Okay, now the question, now we actually get to the actual answering of the question. It says 1, what is the minimum distance this car will stop? Okay, that is xf. Okay, to get the minimum distance you must use the maximum deceleration, and we have that. This is just equal to v. If you solve for xf, you will divide by 2 mu s g. Okay, now the initial velocity is 22.4 meters per second. Square it, 2 times the coefficient of static is 1.1. You multiply that by g 9.8, and you have your answer in meters of 256 meters. So 256 meters is the shortest distance that this car can stop. Question number two, they ask us, what is the stopping distance when the surface is dry and the coefficient is of static friction is 0.6? Okay, so let's just think. will it stop uh, quicker when it's dry or longer? It will stop quicker because there is more friction, and if there's more friction, then its deceleration is more, meaning it'll have a quicker stop. And you can see there, its answer should be for 42.7. Let's just, all we need to do now is just use the same formula, but all we change is the coefficient of friction when it's dry. So that's VI squared 2 mu S G. So that is just 22.4. You only change the changes is 2 times, this is 0.6 now, not 0.1. That's still 9.8. And the answer is 42.7 meters is when it will stop. Okay, 42.7 meters. Okay, so that is question 3. It's quite a nice question. I enjoyed it. Okay, next we need to move on to question number 4 and then 5, and then we're done for today. Okay, so let's move on to question number 4. If there are no questions, if there are no questions, please let's move on to question number 4. Now question 4 says a woman at an airport is towing her 20-kilogram suitcase at a constant speed, so there's no net force, by pulling on a strap at an angle theta above the horizontal. She pulls on the strap with a 35 Newton force, and the friction force on the suitcase is 20 Newton. Okay, so first question, draw a free body diagram of the situation. Okay, so this is the suitcase. Okay, it's being pulled at an angle with the horizontal at an angle of theta degrees. So this is the force applied by the person pulling it. Okay, then it has a normal force. So the normal force, it also has its own weight, so the force of gravity, its weight. And then it has a force of friction, pulling it backwards. That is the force, the free body diagram of this suitcase. Okay, so 2, they want us to calculate. The question asks 2, what angle does the strap make with the horizontal? So they want to calculate theta. What is theta? What angle does the strap make with the horizontal? Okay, what is theta? Okay, so let's plug in what we know. We know that the force that she pulls it with is 35 newtons. So she's pulling with 35 Newton force. The force of friction is 20 newtons. Okay, so the sum of the forces in the x direction, so the forces in the y direction will cancel. So the sum of the forces in the y direction is equal to 0, because the normal force minus the force of gravity is equal to 0. They are exactly equal. Then the sum of the forces in the x direction is equal to mass times acceleration. Okay, this is here mass times acceleration, but there's no acceleration. So mass times acceleration, and that is 0 because she is pulling it at a constant speed. So no acceleration, meaning this, if the sum of the force in the x direction should be 0. So it is the force of friction, so negative the force of friction plus the force applied, and that is the horizontal component of the force applied. it should equal to 0. Now, how do we work out the horizontal component of this force here? Okay, it is the cosine. Okay, it is the adjacent over the hypotenuse to get this force in the horizontal direction of the force applied. Okay, the horizontal component of the force applied. So it is negative 20 for the friction, plus the force applied is 35 newtons times the cosine of theta, and it should equal to 0. Now, if you solve for theta, you will have that the cosine of theta is equal to 20 newtons over 35 newtons. Therefore, theta is equal to 55.2 degrees. So theta is 55.2 degrees. Let's check. So there we have it. Theta is 55.2 degrees. And so we worked it out correctly. Okay. Now they want the normal force. Okay. Question number 3. What is the magnitude of the normal force that the ground exerts on the suitcase? Okay. Now we know that the normal force plus although here I forgot to add here the horizontal component, the vertical component of the forces in the y direction. It also has a vertical component, so this will also be added there, the vertical component of the horizontal of the applied force. Okay, so it'll be the normal force plus the vertical component of the applied force plus minus its weight, which is mg, and that should all be equal to 0. Now we want the normal force. The vertical component of the applied force is none other than the sine of 55.2 degrees, 55.2 degrees multiplied by the applied force of 35 newtons minus its weight, which is just the mass times, is just 20 kilograms times 9,81, and that should all equal 0. If we solve for n, we multiply all of them and then take them to the other side. We have that n, the normal force, is equal to 167 newtons. Okay, and is that what the answer should be? Yes, 167 newtons. Okay, now if we continue, question number 5, which is the last question for today. We have a 40 kilogram child on a swing. Okay, we have a 40 kilogram child on a swing. We have a 40 kilogram child on a swing. So, question number 5. A 40 kilograms child swings in a swing supported by two metal chains, okay, each 3 meters long. The tension in each chain at the lowest point is 350 newtons. Find A, number 1, 5. So, number 1, find the child's speed at the lowest point. Okay, so the tension at the lowest point, meaning when he's directly beneath. Let's say this is the child. Okay, this is the child. I'm going to draw a simple structure. This is the chains. Okay, here is the board or seat of the child. There's the other half of the chain. Okay, now this, when it's at this position, it is at its lowest point. and then of course the swing begins to move upwards this way, and it begins to move upwards that way. Okay, that's how it's moving. Okay, now they want to know the tension in each chain at the lowest point. They're telling us it's 315 newtons. So at this point the tension is 315 newtons. Find the child's speed. At this point the child will have the highest speed, because as he's moving that way he slows down until he stops and then swings down again. And when he moves at his lowest point, he's at his fastest. So now the only forces that act on this child is, let's say this is on this child, is it's his weight, his mass times the gravitational acceleration, and then the tension of the two chains. Okay, tension 1 and tension 2. That is all that is acting on this child at its lowest point. Okay, so the sum of the forces is equal to 2 times the tension minus his weight. Okay, so and that is equal to the sum of the forces is always equal to the mass times its acceleration, and that is what we want. Now we also know that mass times acceleration is equal to mv squared over r. Okay, rotational motion. Okay, so we have these two equations. Okay, so we can actually say that solve for the sum of the forces. Okay, so the sum of the forces is equal to 2t minus mg, which is also equal to mv squared over r. Okay, so that's an equation. So let's work it out. The sum of the forces is equal to 2 times the tension, which is 350 newtons, minus the mass times its acceleration. The mass of the child is 40 kilograms. So 40 times 9,81, and that gives you an answer of 308 newtons. So the net force at that exact point there is 308 newtons upwards. Now solving for V gives us the following. Now in this case, solving for V gives us that V is equal to the sum of the forces times the radius over the mass. Okay, now this thing, if it were to complete a whole cycle, it will make a circle, but at this point it is carving out a section of a circle, which means the radius will just be the length of the chains. So the square root of the sum of the forces is 308, we just worked it out, times the radius is the length of the chain, which is 3 meters, over the mass of the boy, which is 40. Now there are lots of ways you could have done this, but I prefer this one, and the answer gives you at his lowest point the boy moves at a speed of 4,81 meters per second. Right? And let's see if that is correct. 4,81 meters per second. Yes, that is correct. Now, question number 2. They're saying find the force exerted by the seat on the child at the lowest point. Okay, so the seat on the child at the lowest point. So this is the seat. Let's say that's the seat. Okay, Now we have the weight of the child acting on it, this mg, and then we have the normal force opposite to that. Now, since the child is not flying upwards or smashing through the seat, we assume that the normal force is equal to 2 times the tension. Okay? The normal force is equal to 2 times the tension. It must match its weight. Okay? And that is just 2 times 350 newtons, which is just 700 newtons. Okay? So the normal force is, or the force exerted by the seat on the child, which is the normal force, is just 700 newtons. Okay? And that, ladies and gentlemen, is all that I have for today. Thank you for listening. And those of you who are watching this somewhere in the future, I hope you understand. And then if you have, or if you need to, you can just pause the video, just try to work it out for yourself, and then see my method. Now, like one of my lecturers used to say, there are many ways to skin the cat. If you find a faster way, you can do it that way. But this is what I found to be in line with what you've been taught so far. Of course, there are other ways much faster to do this, and it is up to you to find those methods. Okay? After all, the scientist finds the easiest way to get a job done. Okay, someone asked me to explain the force diagram on the seat. Okay, so this is the seat. Okay, I could have drawn it another way. Let me draw it another way and see if you understand it. Let's say this is the let's say this is the seat. Okay. On the seat we will have this way the normal force, and then on this side we will have the force of gravity, or is weight. Does it make sense now? Uh Mr. Cello Kelvin. Uh this is the way I redrew the force diagram. Does it make sense now? The normal force is pushing up against the child, but the child's weight is pushing downwards. Okay, so this is the seat. Okay, the normal force from the seat is pushing against the child, and the child's weight is pushing against the seat. Okay, this is the seat. This is the seat. Okay, the normal force, meaning the force that the. Okay, so you want to know how come the normal force is equal to T? Okay, because the seat here, the seat is not set on anything, it's hanging by the seat here. Let's see, that's the seat, it'll be thin from the side. The seat is hanging by only two forces are connecting. There's a T1 and a T2. So if this is the seat, then the normal force is equal to the force holding the seat upwards, meaning this force, the normal force, is the force pushing against the child. The child's weight, or the force of gravity of this child, the child's weight is pushing the seat downwards, and the normal force is exerting a force upwards. Okay, now this normal force is none other than these two tensions combined. Okay, it's the force that is equal, that is actually providing the normal force. Okay, it is actually holding this thing steady. It is the force that is equaling the normal force. Does that make sense, Cello? Okay, does it make sense that the normal force is pushing against the child, it's holding the child up, but the normal force is being provided by these tensions here? Can you just let me know? Okay, so now we know that the normal force is actually 2t. Okay, thank you. Okay, if you're watching this at a later stage, and then I hope you actually watch this part where I explain why 2 is equal to that. Okay, thank you everyone for watching. I will see you when I next week. Okay, and then 2 more weeks, and then I will be seeing you face to face. Those of you who have FEV 101. Okay, enjoy the rest of your evening. Bye bye.